Hi, my name is Darius Davis, and I did my paper on elliptic curve cryptography. And elliptic curve cryptography is one of the most powerful but least understood types of cryptography and wide use today. At Cloudflare, we make extensive use of ECC. That's the uh when you break it down, little initials for it, to secure everything from our cousin's HTTPS connections to how we pass data between our data centers. Fundamentally, we believe it is important to understand the technology behind any security system in order to trust it. To that end, we look around to find a good, relatively easy to understand primer on ECC in order to share with our users. Finding none, we decide to write one ourselves. This is what follows. B1. This is a complicated subject and it's not possible to boil to a pity blog post. In other words, settle in for a bit of an epic because there's a lot to cover. Okay, so ECC is the next generation of public key cryptography, and based on currently understood mathematics, provides a significantly more secure foundation than generation public key cryptography system like RSA. If you're worried about ensuring the highest level of security while maintaining performance, ECC makes sense to adopt if you are interested in the details read on. The history of cryptography can be split into two eras: the classic era and the modern era. The turning point between the two occurred in 1977 when both the RSA algorithm and the Diff-Hellman key exchange algorithm were introduced. The new algorithms were revolutionary because they represented the first viable cryptographic schemes where security was based on the theory of numbers. It was the first to enable secure communication between two parties without a shared secret. Cryptography went being about securely transporting secret code books around the world to being able to have properly secure communication between any two parties without worrying about someone listening in on the key exchange. Modern cryptography is founded on the idea that the key that you use to encrypt your data can be made public, while the key that is used to decrypt your data can be kept private. As such, these systems are known as public key cryptographic systems. The first and still widely used of these systems is known as RSA, named after the initial of the three men who publicly described the algorithm: Ron Ravis, A.D. Shamir, and Leonard Alderman. What um Alderman. Ooh, wait a minute. Yeah. What you need for a public key cryptography system to work is a set of algorithm that is easy to process in one in one direction but difficult to undo. In the case of RCA, the easy algorithm multiplies two prime numbers. If multiplication is the easy algorithm, it's difficult to pair algorithm is favoring the product of the multiplication into its two component primes. Algorithms that have this characteristic, easy in one direction, hard the other, are known as trapdoor functions. Finding a good trapdoor function is critical to making a secure public cryptography system. Simplistically, the bigger the spread between the difficulty of going one direction in a trapdoor function and going the other, the more secure a cryptographic system based on it will be. The RSA algorithm is the most popular and best understood public key cryptographic system. Its security relies on the fact that factoring is slow and multiplication is fast. In general, a public key encryption system has two components: a public key and a private key. Encryption works by taking a message and applying mathematical operations to it to get to a random looking number. Decryption takes the random looking numbers and applies a different operation to get back to the original number. Encryption with the public key can only be undone by decrypting the private key. Computers do not do well by arbitrarily large number. We can make sure that the number we are dealing with do not get large by choosing a maximum number and only dealing with numbers less than the maximum. We could treat the numbers like the numbers on an analog clock. Any calculation that results in a number larger than the maximum gets wrapped around to a number in the valid range. In the RSA, this maximum value, call it max, is attained by multiplying two random prime numbers. The public and private key are two specifically chosen numbers that are greater than 0 and less than the maximum value. Call them pub and pri. To encrypt a number, you can multiply itself by pri, multiply by itself pub times, making sure to wrap around when you hit the maximum. To decrypt a message, you multiply it by itself pri times and you get back to the original number. It sounds surprising, but it actually works. This property was a big breakthrough when it was discovered. To create RSA key pair, first randomly pick the two prime numbers to attain the match. Then pick a number to be the crypt keeper. As long as you know the two prime numbers, you can compute a corresponding private key prior from this public key. This is how factoring relates to breaking. Factoring the maximum number into its component prime allow you to compute someone's private key from the public key and decrypt their private message. Let this be more concrete with an example. Take the prime number 13 and 7. Their product give us our maximum value of 91. Let's take our public encryption key to know the number 5. Then the fact that we know 7 and 13 are the factors of 91, and applying an algorithm called the extended Euclidean algorithm, we get that the private key is the number 29. These parameters define a fully functional RSA system. You can take a number and multiply it by itself 5 times to encrypt it. Then take that number and multiply it by itself 29 times and you get the original number back. Let's use these values to encrypt the message cloud. In order to represent a message mathematically, we have to turn the letters into numbers. A common representation of the Latin alphabet is UTF-8. Each character corresponds to a number. And that's it.